capacity. If you remember from last year, specific heat capacity is the idea that if you were to leave something like a cup of water out in hot Arizona sun and an iron nail out in the hot Arizona sun for the same amount of time, that both would absorb heat, but they absorb them and show them in a temperature change differently. The water wouldn't feel as hot as a hot iron nail because the nail has a different specific heat capacity. On your paper, you have the definitions. You can see that specific heat capacity is represented by the letter C. It's in the unit of joules per gram Kelvin, this year in Kelvin, not in Celsius. And the equation for specific heat capacity is going to be Q equals mc delta T. The Q will be in joules. The mass will be in grams. Specific heat capacity, we said, is in joules per gram Kelvin. And the temperature change will be in Kelvin. Kelvin, 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 Kelvin. No Celsius. Got it? Good. Now, we use that equation if you're only talking about one substance's temperature changing or calculating the amount of heat produced or transferred. But when you have two substances, you're going to use the idea that if one loses the heat, the other one must be gaining it. So the equation is just mc delta T equals negative mc delta T, because heat lost by one substance is gained by the other. Please notice there is a negative sign here. That negative is showing that one substance is going to be gaining and one substance is going to be losing. It doesn't matter which side you put which substance. Okay, mathematically it's going to work out. Just make sure one side of the equation is in fact negative. Now you see down at the bottom of your paper a bunch of specific heat capacities. Those are there to help you during homeworks. You can always use that as reference. Notice the specific heat capacities are given in joules per gram Kelvin. Again, temperature has to be in Kelvin. You do not have to memorize these. Again, they'll be given to you. The only one you have to know is the specific heat capacity for water. Water's specific heat capacity is 4.184 joules per gram Kelvin, and they do expect that you know that for yourself, so please make sure that you learn that. Alright, so let's do sample problem number 1. If you already did the example problems and you already got the correct answers, then you can stop listening to the pencast in just 1 second. The only other thing I want to say is that you do need to list your givens in addition to your equation. So please make sure that your givens are listed. Other than that, if you have the answers to questions 1, 2, and 3 done correctly, then you can go ahead and just move on to your homework. For those of you that would like a little help, so for number 1, the mass of the copper is listed at 55.0 grams. Specific heat of copper, you can look up on the table on the front, is 0.385 joules per gram Kelvin. The initial temperature of the copper in the problem, it says, is 99.8 degrees Celsius, and the final temperature is 24.5 degrees Celsius. Now we do need to convert these into Kelvin. You do not have to show your work for that process, or you can just do it like I'm doing right here. So we're going to get 297.5 and 372.8. Alright, then you're going to show your equation, which is Q equals mc delta T. We're solving for heat, so Q, the mass is 55. The specific heat is 0.385. And delta T is always final minus initial. So 372.8 minus 297.5. Plug all of that in your calculator and round to 3 significant figures. You're going to get negative 1,590 joules. That's how much heat was lost by the water. That's what this negative is saying, is that it was lost. Then part B asks you how much the water gained. Well, if you know that the metal lost 1,590 joules, then you know that the water gained 1,590 joules. That's all you have to do. Or you could have gone back and plugged it in, but it's easier than that. Alright, number 2, we should have our givens listed. Please make sure that you've written out your givens. To make this as short as possible, I'm going to skip that part. So you're going to write your equation, Q equals mc delta T. Your Q for this problem was in joules already, so we're going to have 64.2, 25 for our mass. The specific heat capacity we don't know, and then our temperature change is already in Kelvin, so 79 minus 78. So solve for C, and you end up with 2.57, and the unit will always be joules per gram Kelvin. Okay, number 3 has two different substances being exchanged. So I would make a list of givens for copper and a list of givens for water. Again, I'm going to skip that step just to make this go a little faster for you, but please make sure that you always have your givens listed. So we're going to have MC delta T equals negative MC delta T because there's two different substances. I'm going to make the right side for water, the left side for the metal, but it's okay if you did it the other way. So we have 34.5, we have 0.385, and then final temperature minus initial temperature. Now we don't know the final temperature, that's what we're solving for. So I'm going to leave that as my variable. Now on the other side, I'm going to have negative 138, well it actually should be there. It's negative of all of these things multiplied. 4.184, again TF. Now notice there's two TFs. The final temperature is going to be the same for both substances because you're putting them in contact with each other and letting them come to thermal equilibrium. So it's the same TF. If it's easier for you just to call it X, that's absolutely fine. Just make sure you do something to solve for your variable. So I'm going to go through and write out how to do the math here. For those of you that are having any difficulty, I would start by multiplying 34.5 times 0.385. So that's going to be 13.283 times our TF minus 371. You don't have to show all these steps, but you can show whichever ones make you feel comfortable and ensure that you don't make silly math mistakes. Now from here we need to distribute. So it's going to be 13.283 times TF, and then multiplying those other two, we're going to get 4,933.3. Then on this side, subtract, oops, nope, it's a negative and a negative, so I'm actually going to be adding 166,519. I believe my work says 0.8528. That might be slightly wrong. I apologize if it is. And then 590.6745 times TF. I'm just combining like terms. So I added over the 577.39. And I'm going to add over the 4,933. So I get 1,71452.9733. So TF is going to equal 290 Kelvin. We should have a bar because we need 3 sig figs. Now I will tell you, people will make math mistakes, so take your time. It may take a lot of work, there's a lot of numbers written there, but if you do it slowly, then you shouldn't have any issue.